Hey, this highlight video is going to be on the conformations of alkanes. So in this video, what we're going to really be doing is to take the molecules out of the paper where we draw them or read about them, and we are going to consider their dynamic nature. So this is one of the favorite things, my favorite things to do in organic chemistry, to look at molecules from different angles, to rotate them, and just play around with them. One thing that helps to do this kind of problem is to have a molecular model kit, which is essentially a small kit of like Tinker Toys, which we can rotate bonds and visualize them, and this might help a lot. I'll show you how to use them in a minute. So after you've watched this video, you should be able to draw Newman projections. So these are a new way to draw structures, which allows us to look at the different conformations and to predict their relative stabilities. All right, so let's review just a little bit here. Before you watch this video, you really should have already read about conformations. Conformations, remember, are structures that differ only in their rotations around sigma bonds or around single bonds. So we're not going to break any bonds, we're not going to move any electrons. All we're going to do is rotations around bonds. The Newman projections, so this type of drawing is a good way to analyze these conformations. And before you go on, you really should understand these following concepts. Dihedral angles, staggered versus eclipsed, anti versus gauche, torsional and steric strains, and what are energy minimum and energy maximums. All right, so if you don't know these terms, go back to the text, read about them, and then we can go forward. So I will do a little bit of review. And so watch this video that I've made using my molecular models to help you understand these. Let's work a couple of problems that are going to be similar to what you will see on exams. So this is an important type of problem. So let's read this out. Draw the most staggered, most stable staggered, and the least stable eclipsed conformations for the C2-C3 bond of 2-methylbutane. So there's a number of things you have to be able to do in this problem, right? You need to know what 2-methylbutane is. So the first thing I would do is just draw out 2-methylbutane. So you can draw it in various ways. I'm just going to draw it. Here's butane, 2-methyl, if I'm counting to the left, 2-methyl would go right here. Okay, so this is 2-methylbutane. So let's think about how we would number this when we're naming. So it would be 1, 2, 3, 4. So what we want to do in this problem is draw a Newman projection. I don't really say that in the problem, but draw a Newman projection looking down the C2-C3 bond. So we want to look at the molecule from this direction. So we're going to put our eye right here. We're going to look down the axis of that C2-3C bond. So the next thing that I would do is I would make sure to fill in all of the bonds that we need to draw this. So I would add in wedges and dashed lines. I'm just going to arbitrarily make this a wedged bond to a methyl group there. I'm going to draw in this methyl group here. And so we would have another hydrogen on the dashed line, and we would have 2 hydrogens on C3, one with a wedged bond and one with a dashed bond. And so now we can see the tetrahedral nature of each of those carbons. So in order to draw our Newman projection, we can see all of the different groups. All right, so remember, in a Newman projection, we draw a dot for the carbon in front. So this is going to be carbon 2. And if my head is up here, so here's my eye and my nose. Oops, my nose is going to be down here. Okay, so carbon 1 is going to be going directly down. All right, the methyl group attached to carbon 2 has a wedge, so if I'm looking at that direction, that bond is going to be going out to my right, and the hydrogen on the dashed line is going to be going to my left. All right, so remember that carbon 3, or the carbon in the back, is going to be drawn as a circle. We just draw it as a bigger circle so we can see it. The methyl group at carbon 4 is pointing in the opposite direction of carbon 1, and so it's going to go up like this. And then the two hydrogens on carbon 3 are going to go one to the left and one to the right. Okay, so this is our Newman projection. Remember, this type of structure or conformation here is called staggered, because all of the bonds on the front carbon and those on the back are alternating one another. Okay? So this is staggered. Some of the important interactions that we need to know between the different groups. Remember, as we look down this bond here from one methyl to the other, this is called the dihedral angle. And when this angle is 60 degrees, like between those two methyl groups, this arrangement of these two groups is called gauche. So that's a 60 degree dihedral angle between two groups. The dihedral angle between this methyl group and this methyl group here is 180 degrees, and this is called anti. All right, when we have groups that are gauche, because those are closer together, the H's on those methyl groups would be starting to push closer together, and it would create what's called steric strain. All right, and that raises the energy of the conformation. So what we see is we have one gauche interaction in this conformation. So what we can do to draw other conformations is to keep one of those carbons the same. I'm going to keep the carbon in front, the carbon with the dot, the same, and I'm going to rotate the one in the back. Okay, so let's go up this way, and so I'm going to keep the one in front the same. So we have one methyl group going down, one to the right, and the H over to the left. I'm going to draw my circle here, and what I'm going to do in this case is I'm going to rotate this methyl group over to the left. I'm going to rotate it by 120 degrees, and so it's now going to be between this hydrogen and the methyl group. This hydrogen down here is going to rotate over to the right, so it's going to be over here. Remember, that line goes directly to the circle, and this hydrogen here is going to rotate up like this. So what I've done is just rotated the back carbon relative to the front one, just like I'm spinning a propeller. Okay, so this gives us another conformation. And then I'm going to draw one more. I'm going to rotate that back carbon one more time. So let's do this one more time. I'm going to keep the front carbon the same. And the back carbon is going to rotate again. So now I'm going to have this methyl group here, H on the top, and the H over here. Okay, so these are three possible staggered conformations looking down the C3 bond of 2-methylbutane. So what we need to do is look at these three structures and determine which one is going to be the most stable. All right, so what we need to look at there is we need to look at the different steric strain interactions. So here we have this gauche interaction creates steric strain. Let's look at the structure on the upper right. Well, here's two methyl groups together, so that's another gauche interaction creating steric strain. And what about the one on the bottom? Here's a gauche interaction, and here's a gauche interaction. So, for these three, this one down here is going to be the highest energy, or it's going to be the least stable. And these two here would be the same energy because they both have only a single gauche interaction. So either of those two structures could be drawn as the most stable. So let's just say here most stable or most stable. All right? So the next part of this is to draw the least stable eclipsed. All right, so remember, eclipsed is where the bonds line up, right? Just like the sun and the moon. If we have a solar eclipse, then the moon lines up with the sun. All right, so what we need to do again is keep one of those carbons the same. Let's just keep this front carbon the same again. And we'll rotate the back one. So what I'm going to do is rotate the back carbon to the right so it lines up with one of these methyl groups. So here's this methyl. We've lined it up so that these two hydrogens line up and another hydrogen lines up here. Oops. Okay, so this is eclipsed. And the highest energy one is going to be where these two methyl groups are eclipsed to one another. So this is the highest steric strain. Okay? So in this molecule, we could have two of those possible structures. And so this structure is going to be the least stable eclipsed. All right, so we want this structure and one of these two structures. All right, let's try one more problem a little bit faster. Okay, in this case, we're going to draw the most stable structure, staggered, and least stable eclipse, just like we did before, but this time we're going to add one more methyl group. We're going to do this on 2,3-dimethylbutane. All right, so we draw our structure. And I'm going to draw the two methyl groups, one at the 2 position and one at the 3 position. So here is a structure of 2,3-dimethylbutane. So like before, what we need to do is draw in our bonds as wedges and dashed lines. So I'm going to, like I did before, I'm going to draw this one. This is arbitrary though. You could do this as either a dash, you could do this one as a dashed line, but I'm going to draw it as a wedge, and my H as a dashed line. So let's just draw in these CH3s so we remember what's there. Alright, so now the other methyl group I could draw either way as well. I'm just going to choose arbitrarily to draw this one also as a wedge, and our hydrogen as a dashed line. I'll draw in this methyl group as well. Alright, so we're going to do the same thing as we did before. We're going to look at it down this C2, C3 bond. The front carbon is just the same as before. We have a CH3 going down. We have a CH3 going to the right. And we have an H going to the left. On the back carbon, we have this CH3 going up, just like before, but the difference is now is that this methyl group here is going to be where we had an H before. So if that's a wedge line and I'm looking down this bond, that methyl group will be out here to the right. The H will go to the other side. All right, so let's look at this structure and analyze for the presence of gauche interactions. All right, so we see one here, we see one here, and we see one here. So this one has 3 gauche interactions. So can we do better than that for a staggered conformation? So let's try one additional structure. We're going to rotate the back carbon just like we did before. So we're going to rotate this. I'm going to draw the front carbon just the same as before. Okay, and the back carbon, we're going to rotate this, and I'm going to rotate this clockwise. Okay. Okay, so the methyl group rotates over here. The top methyl group rotates over here. And the H rotates up here. Okay, so now how many gauche interactions do we have? We have one here. One here. And one here. Oh, dang, it's the same. All right, we're going to have to try this again then. Rotate one more time. Okay, so, oops, this is a CH3 down here and an H over here. We're going to rotate the back one more time, and so we're going to have a CH3 up here, a CH3 over here, and an H over here. And so what type of gauche interactions do we have now? Okay, now we have a gauche interaction here and one here. We only have 2 gauche interactions. Right, so this one is going to be more stable. Lower energy because it has less steric strain. All right, so let's draw the least stable eclipse then. All right, so the least stable eclipse is going to be the one that has the most steric strain. And that means that the biggest groups are going to be eclipsed to one another. All right, so that means if we have 2 methyl groups on the front carbon, they're going to be eclipsed with the 2 methyl groups on the back carbon. So I'm going to have 2 methyl groups together like this, and then I'm going to have 2 methyl groups. Remember, when we draw one to the side of the other, all we're doing is really cheating just a little bit, because in our real structure, the front bonds are just in front of the ones that are in the back. Right? They're eclipsed. Okay, so now we have these 2 eclipsed and these 2 eclipsed, and so this one is going to have the most steric strain. So this is going to be the highest energy. Okay, so try a couple of these problems, see if you can do them on your own.